Hey, it's Mr. Saltano. This video is going to explain single replacement reactions. So, our generic equation, just in general, like the ones we've been looking at before, is A plus BC reacts to forms AC plus B. So, in other words, typically we have an element alone, A, only one type of atom, right, reacting with a compound that's at least two types of atoms that are chemically bound. And what's forming is a new compound, AC, and a different element alone, B. So if we kind of watch what happens here, we can see A plus BC is our original, and then watch what happens over the course of the reaction. Now that becomes AC, and B is alone. And a really useful way to think of this, which will be really useful later on in the video, is to think of these as A is alone, B and C are dancing, and then A disrupts their dance. A is tapping on the shoulder of B, tells B to get lost, and now A and C are dancing, and B is walking off alone. It's going to be really useful later on. So here's a real-life example of this. So if we look at our chemical equation here, we see that it says solid aluminum reacting with aqueous copper 2 chloride to form aqueous aluminum chloride and solid Cu, so solid copper. That's what's happening on top here. So here we have our solid aluminum. We're all used to aluminum foil, right? So that's solid aluminum. And it's reacting with aqueous copper 2 chloride. So in our cartoon version, we can kind of see here that's copper bound with 2 chlorine atoms. And they're actually dissolved in the liquid. That's what makes this actually blue color. What's really happening that we'll talk about later on is that it's actually copper is splitting into ions. Copper is becoming 2+, and the Cls are actually floating around as Cl-, to make this blue solution. So dissolved copper as ions makes a blue solution. When the aluminum goes into the solution, then what happens next is that you see the aluminum is actually bumping out the copper. So our new product that's forming, the clear liquid now, is actually aqueous aluminum chloride. So we can see there's AlCl3 down here. Technically that's actually ionized too. It's not actually together as a compound. But just to make it simpler for now, we're looking at it that way. So the clear liquid is AlCl3, dissolved in water, right, aqueous. And copper is our new solid that forms. So this looks a little bit more like the copper metal that we're used to, like a copper penny. It's not exactly the same texture and look, but it's more similar. That's essentially what we're forming. We're forming solid copper. So the important thing is that we had the bump out happen. Aluminum bumped out copper, and so now because the copper is alone, we see more of a copper color. On top here, this is still aluminum, right? This hasn't reacted yet. So before we started with aluminum metal, reacting with a copper chloride solution, and then we formed an aluminum chloride solution which is actually clear and solid copper. So we can see Al bumped out Cu, and then Cu is on their own. If you look really carefully, you probably noticed that we had CuCl2 and we have AlCl3. Why is that? It's because the copper is a 2+ charge and the aluminum is a 3+ charge, and the chlorines are always a 1-. So we have to make the charges neutral, just like we've seen in the past. Okay. So let's look at a simulation of a very similar reaction, this time copper reacting with silver nitrate. The copper is metal, and the silver nitrate, the copper is solid metal, a metal plate of copper, and the silver nitrate is aqueous, so it's actually dissolved in water, meaning it's split up into ions. It's Ag pluses and NO3 minuses that are broken apart. So let's look at that. So watch carefully. We got our copper atoms going in, and it's reacting with our aqueous solution. Going to zoom in to see what's happening at the molecular level. Now we can see these aqueous Ag pluses floating around, and they're reacting with the copper, and then when the copper breaks off from the solid copper, it becomes Cu2+, which is actually now aqueous. It's dissolving in the liquid. And eventually we get to the point where all of the silvers have reacted, so there's no silver left, essentially floating around, and you just have copper ions floating around. But the most important thing is that we're seeing the silver come in and replace some of the coppers. Every time you see a silver go in, a copper is leaving as well. Also notice that the solution is gradually getting bluer because of all the Cu2 pluses floating around that made the solution blue. And if we zoom back out, this is what it looks like on the macro scale. So again, we can kind of see we've got our compound reacting with our alone element, and then the element comes in and bumps out part of the compound. So in this case, the copper bumped out the silver, Ag, and now silver is on its own as a solid, and we can see that solid silver down here. It's a silver color. And the CuNO3 is actually aqueous, so there's Cu ions floating around in the solution. Okay. And here's just another example. Fred and Wilma are together. Betty is a homewrecker, bumps out Wilma, and now Fred and Betty are together with Wilma alone. Just a couple of other examples here. These are some pretty cool reactions that happen. But again, all we're seeing is that the element is coming in and bumping out part of the compound. Something else to note is that typically a metal will bump out only another metal, but it could also bump out hydrogen as well. That's the only exception. And here we're seeing that again where Na comes in and bumps out H, and now we're left with NaOH, and the H is by itself. So here's another real-life example where you have magnesium solid reacting with silver nitrate, which is dissolved in water, to form magnesium nitrate, which is dissolved in water, aqueous, and solid silver. Now, the last part of this video, something else that's really important, is that this reaction doesn't always happen. You can't just throw together any element and any compound and have it work. There's actually a list that chemists have made, though, that we can check to see whether this is going to work, and it's called the activity series. Here's an example of like a reaction that doesn't work. So actually, if you put these two together, nothing would actually happen. So what happens is a metal will displace another metal based on the list, and also a nonmetal will displace another nonmetal based on the list. So let's take a look at that list and see what I'm talking about. So in this first reaction here, we're looking at the incoming guy is a metal. So that means that if it's going to replace anybody at all, it's going to be another metal that's part of the compound. So I've underlined those just to clarify. And if we check our list, the most reactive metals are at the top, and as you go down, they become less reactive. So the simplified way of saying is that if the metal is higher on the list of our activity series, that means it will in fact bump out the other metal that's part of the compound. The other metal that's part of the dance will essentially be replaced. So if we check this, we're comparing magnesium to silver on our list. So magnesium is the alone guy. We want to see if it's replacing silver on the list. So here's magnesium, it's up here, and silver is all the way down here. So that means that yes, magnesium actually will replace silver, and because that replacing will happen, that means yes, boom, that is a reaction. A chemical reaction would occur. Let's look at a counterexample though. Here we still have magnesium coming in as the one who's potentially trying to disrupt the dancer, but now we're comparing it to lithium. Now remember I said this metaphor for dancers is going to come in handy again? Well, that's because think about that in real life. If someone's coming in to disrupt a dance, if the guy who's already dancing is stronger, aka more reactive, the dance isn't going to be disrupted. So if you have like this really huge tough guy who's already dancing, he's not going to take kindly to some other littler guy coming in and just trying to break up him and his date, right? So if we look at this one, magnesium is the guy who's coming in and trying to break up the dance, and now he's picking on a bulkier, more reactive guy. So lithium, and by the way, he's not literally bigger, but he's more reactive. Lithium's at the top of the list. So this magnesium is trying to pick on the head honcho. So it's not going to work. Any incoming alone metal trying to disrupt another metal isn't going to be successful if that metal it's trying to break up the dance with is higher on the list, if it's more reactive. So that's all you really have to check. First you check what's coming in. If it's a metal, you compare it to the other metal in the compounds. It's usually the first one listed in the formula. If the guy who's alone is higher on the list, on the VIP list, then he's going to bump out the other dancer in the compound. But if the guy who's coming in alone is lower on the list than the one who's already dancing, it's not going to happen. No reaction will happen. You can literally have them sit there for an eternity and you wouldn't see anything happen in that reaction. Okay, one last thing and then we're just about done. This can also happen with the halogens. So remember, the halogens are the nonmetals, specifically in that second to last column at the right of the periodic table. If the incoming element is a halogen, then we're not going to compare it to any metals, we're going to compare it to another halogen. So if we look at this reaction, chlorine is a halogen, right? So we're comparing it to iodine, another halogen that's part of the compound. The question is, will it disrupt the dance? Halogens have sort of their own activity series, but this is also how it's listed on the periodic table as well, so it makes it easy. If you look at that column, it happens to fall in the same order. So we check, is chlorine higher than iodine, the other halogen, on the list? And yes, it is. So boom, that reaction would happen. The bump out would occur. And again, we're only comparing halogens. If a halogen comes in, you compare it to another halogen. Now we're checking the reverse. Would this other reaction happen, the exact opposite reaction, where if iodine's coming in, would it bump out Cl2? So let's see. So iodine's coming in, it's lower on the list, it would not bump out Cl. So no reaction would occur in that case. Which, if you think about it, kind of makes sense, because then after this left reaction happened, it would go backwards. It would be going back and forth forever, right? So only one reaction is really going to happen, and it's going to go all the way when that happens. So the key things here, you want to use the activity series. This only happens for single replacement reactions. You want to see whether it will happen, and in order to do that, you have to see whether the incoming element is a metal or not. And then if it's higher on the list of metals, and if it's a halogen that's incoming, then you see if it's higher on the list of halogens. So that's it for the single replacement reactions. Thanks for watching, and remember, chemistry is everywhere.